Okay, chapter 13, talking about the reaction rates, which is called kinetics. We will also talk about the effect of concentration of the molecules, effect of temperature, and a little bit about effect of pressure on the rate of reactions. This is personally one of my favorite chapters. I hope you enjoy it too, you find it interesting, which you have it in daily life also. So let's start with reaction rate. Let's say we have a reaction between A and B, which is going to produce C and D. A and B are your reactants and C and D are your products. So by preceding the reaction, what happens? You have a decrease in the concentration of reactants and increase in concentration of products, right? So first of all, the concentration, the molar concentration, we show it in two brackets. It's going to show molar concentration. You will have this in the next chapters also, the future, so learn it. The brackets show the molar concentration. Now, if we want to express the rate of reaction based on diminishing or decreasing the concentration of A and B, we can write it as rate is. Tell me in physics, what is the rate? You remember, rate was the distance over time, right? The change in the distance over the change in time. But of course, for the chemical reactions, molecules do not do not pass any distances. Instead, their concentration changes. So for the reactants, the rate, we said it decreases, right? So we need a negative sign. The negative sign shows the decrease in the concentration. The change, delta, in the concentration of a reactant over change of time. Or if you want to write it for the other reactant, you will have the same minus delta concentration of B over delta T. On the other side, if you want to write the rate based on C and D, how would you write it? We said for the products, the rate is going to be increasing, the concentration is going to be increasing. So it's positive delta C over delta T. Or if you, similar for D, if you want to write it, it's positive. You can eliminate positive, but you cannot eliminate negative. So make sure you show negative, but it's okay if you eliminate positive positive sign. Delta concentration of D over time. All right, that's how you write the rate. Now let's work on a real example you have on slide number 19. Let's write a real reaction. The reaction is 2N2O5 gas molecules will decompose to 4 NO2 gas molecules plus oxygen. So in order to write the rate of formation of oxygen, how would you write it? Oxygen is a product, so it has to increase. Let's just simply eliminate the positive charge. Concentration of O2 over change in time. Okay? rate of formation of NO2. And let's be more accurate. Let's include the stoichiometry coefficients because it matters in the rate. So we said positive, but it's inverse of the coefficient. If the coefficient is 4, so it's 1 over 4. For in case of oxygen was 1 over 1 that we didn't show. And it's delta concentration of NO2 over delta T. Let's take care of rate of disappearing or decomposition of N2O5. Rate of decomposition of N2O5. What is the coefficient? 2. And so it would be 1 over 2. That's the reactant, so you need to show the negative sign and delta N2O5 over delta T. That's how you determine the rates of formation of products and rates of decomposition of the reactants considering their stoichiometry coefficients. So you can simply, if you want to relate these rates to each other, you can say delta concentration of oxygen over time is 1/4 of delta concentration of NO2 over time, which is equal to minus you'll definitely have a question about this in the exam just by looking at the coefficients and inversing them, considering the product positive, reactant negative, and they all will be equal to each other. So it shows that the rate of disappearing the N2O5 inverse of half of it is equal to the delta concentration, the formation of oxygen, and 1/4 of concentration of NO2. The next thing you need to know is how to write the rate equation. Or before that, let's work on an example that you have. I don't want to miss it. You have it on slide number 24 of your PowerPoint files. It says peroxy disulfide ion oxidizes iodide ion to triiodide ion. The reaction is S2O8 plus, save the time, I just don't write the physical states because they don't matter here now, plus triiodide. What are we supposed to do? How is the rate of reaction that is expressed as the rate of formation of triiodide? Triiodide is a product, right? So the rate is going to be how is the rate of reaction that is expressed as the rate of formation of iodide related to the rate of reaction of iodide? So rate of formation of this triiodide, we wrote it, it's a product, so it's going to be positive, relating to the rate of reaction based on iodide ion. It's a reactant, so first of all we have negative sign, and then inverse of the stoichiometry coefficient. And then delta iodide over time. Now, if you have any numerical values, you can easily plug them in. The next question on slide number 25 is saying calculate the average rate of formation of oxygen in the following reaction during the time interval from, let me find it, where is it? Sorry, I'm trying to. Okay, so it's asking for concentration of O2 is going from, first of all, time is 1200 second goes to 1800 second, and at this 1200 second concentration of oxygen is 0.0036 molar. At 1800 second, this concentration is going to change to 0.0048 molar. Then we are supposed to find the average rate of formation of oxygen in the following reaction during this change. So we can say they were supposed to give you the reaction, but it's missing. I don't see it there, so doesn't matter. It says rate of formation, so oxygen is considered as the product, and so we say rate is, we consider it one, the stoichiometric coefficient, since there's no more information. So it's delta formation of oxygen, delta concentration of oxygen on over delta T. Delta, or change in the concentration of oxygen, is 0.0048 molar minus 0.0036 molar. And you see, it makes sense because it's the rate of formation, the concentration is increasing. Over delta T is 1800 minus 1200. So the rate is going to be, and this is sec. This is going to be 2 times 10 to negative 6 molar per second. So you learned one more thing here besides calculations of the rate, is that the unit for rate, because it's delta concentration over delta T, what is the unit for concentration? Molar, right? And what is the concentration, what is the unit for time? T. So the unit for rate is molar per second, or you can see it as molar is moles per liter, right? Mole per liter second. Keep it in mind. It will be handy later on. All right. The next thing you need to know, the next basic thing you need to know about the rate of the reactions is that we write a rate law about each reaction, and the rate law gives you some information about the reaction. So let's say you have this equation. What if I tell you rate is written as this? There are some points that I want you to be careful and pay attention really, really carefully. K is the rate constant. And you have it in every single rate law. This is the rate law, or rate equation. Let's call it just rate law. All right. And you see that rate law is only written for reactants. Only for reactants. You never can find a rate law in which you see the products. As you see here, you see the reactants, the molar concentration of the reactants. And the last but not least, you might have expected to see lowercase a and lowercase b as the exponents, but that's not the case. Whatever exponent they have, they are stoichiometric coefficients. But these m and n are orders of reaction for A and B, and we will talk about it again, and we will determine them, and we have more to talk about these. M plus N is called overall order of reaction. So, one more time, rate law is shown in this form. First of all, you need the rate constant, and then the concentrations, the molar concentrations of the reactants to the powers of the numbers that are not necessarily the same as their coefficients. They are called the order of reaction towards A and towards B, and if you have more reactants. The sum of the reaction orders is called the overall order of reaction. So our goal is to determine M and N, and if we have any other order, and then add them to each other to find out the overall rate of reaction. Let me see if we have any. Yeah, let's see. Let's work on a real example from your book. Slide 31. You have 2 NO2, the gaseous form, plus 1 fluorine molecule in gaseous form. They react to form 2 NO2F in gaseous form. That's the reaction. And the rate law is given. The rate law is K NO2 F2. And I will tell you how to determine these numbers later. You will see, if you go by the exponent, you expect to have the coefficient 2 here, but you don't see it there. I told you, these exponents are not necessarily the same as the coefficients. So be careful, they're totally different. Now, this is the given rate law. Let's find out the order of reaction for NO2. Order for NO2 is what you see here that you don't show it. It was 1 that you don't show it, so it's 1. Order for F2 that you don't see it, again 1. You know, we can eliminate 1. Then what is the overall order? 1 plus 1. We said we add them to each other to find the overall order. Is 2. So there can be a question, a simple question about the reaction. So you simply just look at the exponents. If you don't see anything, it's going to be 1. And if you see 2, it's the order is 2. And you simply find out the order for each of the components and find out the overall order of the reaction. We can work on, let's work it together. On page 32, on slide number 32, we have a good example. Slide number 32. H2O2 is added to iodide in the presence of acidic solution, some hydrogen ion. It will give you triiodide plus 2 water molecules. And the rate law is given as H2O2 times iodide. So this is the given rate law. We are supposed to find the order of reaction with respect to each reactant and then the overall order. So let's just check the orders with the rate law. What is the order for H2O2? What do you see here? 1. Order for iodide, again, you don't see anything here, so it's 1. And you might have thought that I forgot to write the concentration of hydrogen, but I didn't. This is what is given to you. Order for hydrogen. Do you see anything here? No, means it was 1. So what exponent makes any number 1, changes it to 1, 0. So the order of the reaction towards hydrogen, for hydrogen, is 0. So what is the overall order? 1 plus 1 plus 0 is 2. So the 0th order, you might look a little bit weird too. What is the 0th order? Means that the concentration of the hydrogen here does not have any role in the rate of the reaction. Okay? Because you don't see it here, so doesn't matter if you change the concentration, you double the concentration, add more acid, or take some acid out, it's not going to change anything in the rate of the reaction. That's what 0th order means. And we will talk about the orders of the reactions again. So far, just to let you know that we work on 0th order reactions, 1 and 2 only. We do not make it more complicated. So the orders that you see on the reaction 0, 1, and 2. So it takes us to how to determine the orders of the reaction, because I don't want this video to be too long. Let me continue in the next video. You have enough to practice until the next video, and more information about the reactions.